elements, we have to sum up the entire flux, that is integration of d phi small, that is EDS. So on putting the formula value of this d phi from this equation, next we also know that the flux associated with this area element ds by definition, this is again by definition. Now let's learn Gauss law in detail. Now we will be deriving the condition of the Gauss law. For that we have to assume a sphere or S of radius r enclosing a certain charge q, positive charge q is present on the inside the surface, and now we have to choose an area element ds whose area vector is pointing in a perpendicular direction, pointing in an outward direction, and the electric field E due to this point charge is also pointing radially outward. So what we find here, that electric field is parallel to the area element, that is ds. Both are having the zero angle between them. Now we will be learning about the Gauss theorem, which states that total flux passing through any closed surface is 1 upon epsilon naught times the net charge enclosed by the closed surface. Here Gauss theorem relates the flux with the charge enclosed. So this is the Gauss theorem. We will be proving this Gauss theorem. So here what we are having, the flux associated is q by epsilon naught times the total charge enclosed inside the Gaussian surface. So let us try to prove this situation. So we know that electric field at any point on the spherical surface S at a distance of r, the value of the electric field will be 1 upon 4 pi epsilon naught q by r square. This is the by definition. This is what we are having, the electric field by definition. Next, we also know that the flux associated with this area element ds by definition. This is again by definition. So here it is by definition, the flux associated, we know that it is E dot ds. Here already I have told you E and ds are parallel to each other, so the angle becomes cos 0 degree, so it comes out to be the EDS. Similarly, what will be the net total flux? If we will divide this entire area, surface area into different area elements ds, and we will compute the flux associated with all these small area elements, we have to sum up the entire flux, that is integration of d phi small, that is EDS. So on putting the formula value of this d phi from this equation, previous equation, E comes out of this integration sign because the value of E is constant everywhere on the surface at a distance of r. E we have to take it outside and we have to integrate the small area elements ds and ds. Now next, by definition, whatever we have got it by the electric field, we have to put this value, that is the value of electric field is 1 upon 4 pi epsilon naught q by r square. This is the by definition we have use the formula for electric field. Next, if we will integrate the small area elements over the entire surface, so surface area for the sphere we will get 4 pi r square. This portion we are getting by the integration, and on solving what we find is that the certain terms cancels each other and what we are left is with only q by epsilon naught. That is how we will prove the Gauss theorem. The flux associated with passing through any closed surface is 1 upon epsilon naught times the net charge enclosed by the closed surface. So here I have given all the necessary and the required steps only, in which 3 to 4 steps you can prove this theorem in a nice way and you can present your answer. Now let's derive the Coulomb's law from the Gauss theorem. For that, what we have to assume, that here by symmetry we have to assume a sphere as surface S enclosing a charge q having a radius of r. So here, due to the point charge q, the electric field E will be pointing radially outward, and we have chosen a surface area element whose area vector ds is also pointing radially outward. So here by symmetry what we notice is that electric field E has same magnitude at all points on the S. So by symmetry, electric field at all point, it will be equidistant at a distance of r, so its magnitude will be the same, and E and ds are directed radially outward, and hence flux through such a situation through the single area element d phi E, by definition what we will get E dot ds, and the angle between electric field and the area element, that is area vector, is 0 degree, so it becomes Ed cos 0 degree, and cos 0 degree is 1, so we will get electric flux associated with the area element for this d phi is the EDS. Now if we want to compute the net flux through the closed surface, so by considering the various area elements, small area elements surrounding this surface area, we have to add up the flux element in such a situation that the net flux phi E becomes the integration of d phi E. Now the value of d phi E we have already got from this first equation, so we will keep ED integration of ds. Again we are putting this E is outside the integration because the value of E is same, its magnitude is constant throughout the surface, so it will come out of the integration sign. So we will get E into 4 pi r square. This 4 pi r square is the integration of the surface area elements over a sphere. So this is the surface area of the given sphere. Next, by using the Gauss law. Now the first step we have to use in proving this is, first we have to use the definition of the flux. Second, we have to use the flux by the Gauss law. So only these two equations are sufficient for deriving the Coulomb's law from the Gauss theorem. Next, using the Gauss law, we know that flux associated is total charge Q by epsilon naught. So we have to equate this first and second equation because their LHS side are equal, and now we will equate the two equations. So we will get E into E 4 pi r square is Q by epsilon naught. Rearranging the terms, we will get electric field at a distance of r on the surface is 1 upon 4 pi epsilon naught Q by r square. So now if once we have got this electric field, so now the force on the point charge, if suppose a point charge Q naught is located on this present anywhere on the surface S. Now let us suppose if a Q naught, if a test charge Q naught is present on the surface S, then it will experience a kind of a Coulomb force. The magnitude of that Coulomb force will be the Q naught into E. So now what we will get, we have now derived the formula for the electric field here. So this we will keep the value of the electric field 1 upon 4 pi epsilon naught Q by r square is the electric field into Q naught. But the Coulomb's force between the 2 point charges, that is Q and Q naught. So this is how by using the Gauss law we have derived the Coulomb's law also. So here only you need to keep in mind only the two basic steps. What are the two basic steps? Again I am highlighting the two basic steps is, first use the flux by the definition, and second use the flux by the Coulomb's law. Equate these two equations and then solving you can be able to prove the Coulomb's law from the Gauss theorem. So these are the key points, and these are the only steps that you will present or write in your answers. You will be going to get the full marks. Here the detailed explanation I have already given it to you. Next, certain key points you have to keep in mind. What are the some important key points? These points I have taken from the NCERT book only. So here what is the first key point? Gauss law is true for any closed surface no matter what its shape or size. The surface that we choose for the application is called as the Gaussian surface, and it is often useful towards much easier calculation of the electrostatic field when the system has some symmetry. Here previous in the first point we have told that it is applicable for any shape or size, whatever be the shape or size of the closed surface. But in practice, if we choose a symmetric surface, symmetrically closed surface, then it will lead to the easy calculation. So that should be our priority, that we have to use the Gauss law in a certain special situation where the system has some symmetry. Next, Gauss law is based on the inverse square dependence on distance contained in the Coulomb's law. That is, it is valid where only the Coulomb's law is also inverse square law. So they are two in tuning with each other. That is, it always obeys the Coulomb's law. Any violation of Gauss law will indicate departure from the inverse square law. So whenever we are not having this inverse square law dependence, we won't be able to use the Gauss law. Next, we are having, if the net charge enclosed by a closed surface is 0, then the flux through it is also 0. That is also we have proved earlier. If no charge is enclosed by a surface, the flux will be the 0. The net flux through a closed surface due to a charge lying outside the closed surface is also 0. If the charge is lying outside the surface, then the flux is also 0. These things I have already proved in the concept of the electric flux. Next, the charge Q appearing in the Gauss theorem includes the sum of all the charges located anywhere inside the closed surface. This is a very important key point. The charge Q which is appearing, it is the summation of all the charges that are present only inside the Gaussian surface. It excludes the charges that are outside the surface. But the electric field E appearing in the Gauss theorem is due to all the charges both inside and outside the closed surface. This is again another a very important key point over here. The electric field that we are calculating using in the Gauss theorem, it will be due to all the charges that are inside and outside, because the electric field will be crossing the surface, entering the surface and then leaving the surface, whether the charge is present inside the surface or whether it is present outside the surface. So these are the two important key points the charge is only contributing when it is present inside the surface, but the electric field which is appearing in this Gauss theorem is due to all the charges that are inside as well as outside the Gaussian surface. Okay. However, the charge Q appearing in the theorem is only contained within the closed surface. So this is very important key point. Next, for a medium of absolute permittivity, that means if the charge is present in spite of the space, if it is present in some other medium having a permittivity of epsilon or dielectric constant epsilon r, then the Gauss theorem will be changed to, that is the flux associated, that is E dot ds becomes equals to Q by epsilon, which is the permittivity of the medium, not of the space. And on solving this epsilon, we will get epsilon r into epsilon